Piezoelectricity.
Piezoelectricity piɛizoʊ. Electricity is the electric charge that accumulates in certain solid materials in response to applied mechanical stress. The word piezoelectricity means electricity resulting from pressure. It is derived from the Greek piezo or piezein, which means to squeeze or press, and electric or electron, which stands for amber, an ancient source of electric charge. Piezoelectricity was discovered in 1880 by French physicists Jacques and Pierre Curie. The piezoelectric effect is understood as the linear electromechanical interaction between the mechanical and the electrical state in crystalline materials with no inversion symmetry. The piezoelectric effect is a reversible process in that materials exhibiting the direct piezoelectric effect, the internal generation of electrical charge resulting from an applied mechanical force, also exhibit the reverse piezoelectric effect, the internal generation of a mechanical strain resulting from an applied electrical field. For example, lead zirconate titanate crystals will generate measurable piezoelectricity when their static structure is deformed by about 0.1% of the original dimension. Conversely, those same crystals will change about 0.1% of their static dimension when an external electric field is applied to the material. The inverse piezoelectric effect is used in production of ultrasonic sound waves. Piezoelectricity is found in useful applications such as the production and detection of sound, generation of high voltages, electronic frequency generation, microbalances, to drive an ultrasonic nozzle and ultrafine focusing of optical assemblies. It is also the basis of a number of scientific instrumental techniques with atomic resolution, the scanning probe microscopies such as STM, AFM, MTA, SNOM, etc., and everyday uses such as acting as the ignition source for cigarette lighters and push-start propane barbecues.
History. Discovery and early research.
The piezoelectric effect, by which a material generates an electric potential in response to a temperature change, was studied by Carl Linnaeus and Franz Apenes in the mid-18th century. Drawing on this knowledge, both René Justot and Antoine César Becquerel posited a relationship between mechanical stress and electric charge. However, experiments by both proved inconclusive. The first demonstration of the direct piezoelectric effect was in 1880 by the brothers Pierre Curie and Jacques Curie. They combined their knowledge of piezoelectricity with their understanding of the underlying crystal structures that gave rise to piezoelectricity to predict crystal behavior, and demonstrated the effect using crystals of tourmaline, quartz, topaz, cane sugar, and Rochelle salt, sodium-potassium tartrate tetrahydrate. Quartz and Rochelle salt exhibited the most piezoelectricity. The Curies, however, did not predict the converse piezoelectric effect. The converse effect was mathematically deduced from fundamental thermodynamic principles by Gabriel Lippmann in 1881. The Curies immediately confirmed the existence of the converse effect, and went on to obtain quantitative proof of the complete reversibility of electroelastomechanical deformations in piezoelectric crystals. For the next few decades, piezoelectricity remained something of a laboratory curiosity. More work was done to explore and define the crystal structures that exhibited piezoelectricity. This culminated in 1910 with the publication of Waldemar Voigt's Lübsche der Kristallphysik, textbook on crystal physics, which described the 20 natural crystal classes capable of piezoelectricity, and rigorously defined the piezoelectric constants using tensor analysis.
World War I and post-war.
The first practical application for piezoelectric devices was sonar, first developed during World War I. In France in 1917, Paul Langevin and his co-workers developed an ultrasonic submarine detector. The detector consisted of a transducer, made of thin quartz crystals carefully glued between two steel plates, and a hydrophone to detect the returned echo. By emitting a high-frequency chirp from the transducer, and measuring the amount of time it takes to hear an echo from the sound waves bouncing off an object, one can calculate the distance to that object. The use of piezoelectricity in sonar, and the success of that project, created intense development interest in piezoelectric devices. Over the next few decades, new piezoelectric materials and new applications for those materials were explored and developed. Piezoelectric devices found homes in many fields. Ceramic phonograph cartridges simplified player design, were cheap and accurate, and made record players cheaper to maintain and easier to build. The development of the ultrasonic transducer allowed for easy measurement of viscosity and elasticity in fluids and solids, resulting in huge advances in materials research. Ultrasonic time-domain reflectometers, which send an ultrasonic pulse through a material and measure reflections from discontinuities, could find flaws inside cast metal and stone objects, improving structural safety.
World War II and post-war.
During World War II, independent research groups in the United States, Russia, and Japan discovered a new class of synthetic materials, called ferroelectrics, which exhibited piezoelectric constants many times higher than natural materials. This led to intense research to develop barium titanate and later lead zirconate titanate materials with specific properties for particular applications. One significant example of the use of piezoelectric crystals was developed by Bell Telephone Laboratories. Following World War I, Frederick Alack, working in radio telephony in the engineering department, developed the AT-cut crystal, a crystal that operated through a wide range of temperatures. Lack's crystal didn't need the heavy accessories previous crystal used, facilitating its use on aircraft. This development allowed Allied air forces to engage in coordinated mass attacks through the use of aviation radio. Development of piezoelectric devices and materials in the United States was kept within the companies doing the development, mostly due to the wartime beginnings of the field, and in the interests of securing profitable patents. New materials were the first to be developed. Quartz crystals were the first commercially exploited piezoelectric material, but scientists searched for higher performance materials. Despite the advances in materials and the maturation of manufacturing processes, the United States market had not grown as quickly. Without many new applications, the growth of the United States piezoelectric industry suffered. In contrast, Japanese manufacturers shared their information, quickly overcoming technical and manufacturing challenges and creating new markets. Japanese efforts in materials research created piezoceramic materials competitive to the U.S. materials, but free of expensive patent restrictions. Major Japanese piezoelectric developments include new designs of piezoceramic filters for radios and televisions, piezo buzzers and audio transducers that can connect directly to electronic circuits, and the piezoelectric igniter, which generates sparks for small engine ignition systems, and gas grill lighters, by compressing a ceramic disc. Ultrasonic transducers that transmit sound waves through air had existed for quite some time, but first saw major commercial use in early television remote controls. These transducers now are mounted on several car models as an echolocation device, helping the driver determine the distance from the rear of the car to any objects that may be in its path.
Mechanism.
The nature of the piezoelectric effect is closely related to the occurrence of electric dipole moments in solids. The latter may either be induced for ions on crystal lattice sites with asymmetric charge surroundings, as in BaTiO3 and PZTs, or may directly be carried by molecular groups, as in cane sugar. The dipole density or polarization, dimensionality, may easily be calculated for crystals by summing up the dipole moments per volume of the crystallographic unit cell. As every dipole is a vector, the dipole density P is a vector field. Dipoles near each other tend to be aligned in regions called vice domains. The domains are usually randomly oriented, but can be aligned using the process of polling, not the same as magnetic polling, a process by which a strong electric field is applied across the material, usually at elevated temperatures. Not all piezoelectric materials can be poled. Of decisive importance for the piezoelectric effect is the change of polarization P when applying a mechanical stress. This might either be caused by a reconfiguration of the dipole-inducing surrounding or by reorientation of molecular dipole moments under the influence of the external stress. Piezoelectricity may then manifest in a variation of the polarization strength, its direction or both, with the details depending on 1. The orientation of P within the crystal, 2. Crystal symmetry, and 3. The applied mechanical stress. The change in P appears as a variation of surface charge density upon the crystal faces, that is, as a variation of the electrical field extending between the faces caused by a change in dipole density in the bulk. For example, a 1 cm 3 cube of quartz with 2 kilonewtons, 500 pound forces, of correctly applied force can produce a voltage of 12,500 V. Piezoelectric materials also show the opposite effect, called converse piezoelectric effect, where the application of an electrical field creates mechanical deformation in the crystal.
Mathematical description.
Piezoelectricity is the combined effect of the electrical behavior of the material, where D is the electric charge density displacement, electric displacement, E is permittivity and E is electric field strength, and Hooke's law. Where S is strain, S is compliance and T is stress. These may be combined into so-called coupled equations, of which the strain charge form is in matrix form. Where is the matrix for the direct piezoelectric effect and is the matrix for the converse piezoelectric effect? The superscript E indicates a zero, or constant, electric field. The superscript T indicates a zero, or constant, stress field. And the superscript T stands for transposition of a matrix. The strain charge for a material of the 4 mm, C4V, crystal class, such as a poled piezoelectric ceramic such as tetragonal PZT or bar TO3, as well as the 6 mm crystal class may also be written as ANSIIEE 176. Where the first equation represents the relationship for the converse piezoelectric effect and the latter for the direct piezoelectric effect. Although the above equations are the most used form in literature, some comments about the notation are necessary. Generally D and E are vectors, that is, Cartesian tensor of rank 1. And permittivity E is Cartesian tensor of rank 2. Strain and stress are, in principle, also rank 2 tensors. But conventionally, because strain and stress are all symmetric tensors, the subscript of strain and stress can be relabeled in the following fashion: 11-1, 22-2, 33-3, 23-4, 13-5, 12-6. Different convention may be used by different authors in literature. Say, some use is 12-4, 23-5, 31-6 instead. That is why S and T appear to have the vector form of 6 components. Consequently, S appears to be a 6x6 matrix instead of rank 4 tensor. Such a relabeled notation is often called void notation. In total, there are 4 piezoelectric coefficients and defined as follows. Where the first set of 4 terms correspond to the direct piezoelectric effect and the second set of 4 terms correspond to the converse piezoelectric effect. A formalism has been worked out for those piezoelectric crystals, for which the polarization is of the crystal field-induced type, that allows for the calculation of piezoelectrical coefficients from electrostatic lattice constants or higher-order Madelung constants.
Crystal classes.
Of the 32 crystal classes, 21 are non-centrosymmetric, not having a center of symmetry, and of these, 20 exhibit direct piezoelectricity. The 21st is the cubic class 432. 10 of these represent the polar crystal classes, which show a spontaneous polarization without mechanical stress due to a non-vanishing electric dipole moment associated with their unit cell, and which exhibit pyroelectricity. If the dipole moment can be reversed by the application of an electric field, the material is said to be ferroelectric. Polar crystal classes 1, 2, M, 2, 4, 4 mm, 3, 3M, 6, 6 mm, Piezoelectric crystal classes, 1, 2, M, 222, M2, 4, 4, 422, 4 mm, 42 M, 3, 32, 3 M, 6, 6, 622, 6 mm, 62 M, 23, 43 M. For polar crystals, for which P0 holds without applying a mechanical load, the piezoelectric effect manifests itself by changing the magnitude or the direction of P or both. For the non-polar, but piezoelectric crystals, on the other hand, a polarization P different from 0 is only elicited by applying a mechanical load. For them the stress can be imagined to transform the material from a non-polar crystal class, P equals 0, to a polar one, having P 0.
Materials.
Many materials, both natural and synthetic, exhibit piezoelectricity.
Naturally occurring crystals.
Quartz, berlinite, Alpo4, a rare phosphate mineral that is structurally identical to quartz, sucrose, table sugar, Rochelle salt, topaz, tourmaline group minerals. The action of piezoelectricity in topaz can probably be attributed to ordering of the FOH in its lattice, which is otherwise centrosymmetric, orthorhombic bipyramidal, MMM. Topaz has anomalous optical properties which are attributed to such ordering.
Bone.
Dry bone exhibits some piezoelectric properties. Studies of Furcado et al. Showed that these are not due to the apatite crystals, which are centrosymmetric, thus non-piezoelectric, but due to collagen. Collagen exhibits the polar uniaxial orientation of molecular dipoles in its structure and can be considered as bioelectrate, a sort of dielectric material exhibiting quasi-permanent space charge and dipolar charge. Potentials are thought to occur when a number of collagen molecules are stressed in the same way, displacing significant numbers of the charge carriers from the inside to the surface of the specimen. Piezoelectricity of single individual collagen fibrils was measured using piezo response force microscopy, and it was shown that collagen fibrils behave predominantly as shear piezoelectric materials. The piezoelectric effect is generally thought to act as a biological force sensor. This effect was exploited by research conducted at the University of Pennsylvania in the late 1970s and early 1980s, which established that sustained application of electrical potential could stimulate both resorption and growth, depending on the polarity, of bone in vivo. Further studies in the 1990s provided the mathematical equation to confirm long bone wave propagation as to that of hexagonal, class X, crystals.
Other natural materials.
Biological materials exhibiting piezoelectric properties include tendon, silk, wood due to piezoelectric texture, enamel, dentin, DNA, viral proteins, including those from bacteriophage. One study has found that thin films of M13 bacteriophage can be used to construct a piezoelectric generator sufficient to operate a liquid crystal display.
Synthetic crystals.
Gallium orthophosphate, GaP04, a quartz analogic crystal, langosite, La3Ga5CO14, a quartz analogic crystal.
Synthetic ceramics.
The family of ceramics with perovskite or tungsten bronze structures exhibits piezoelectricity. Barium titanate, BaTiO3. Barium titanate was the first piezoelectric ceramic discovered. Lead titanate, PbTO3. Lead zirconate titanate, PbO30. X. 1, more commonly known as PZT, lead zirconate titanate is the most common piezoelectric ceramic in use today. Potassium niobate, KnBO3, lithium niobate, LiNBO3, lithium tantalate, LiTaO3, sodium tungstate, Na2WO3, zinc oxide, ZNO, Bar2NANB505, Pb2KNB5015.
Lead-free piezoceramics.
More recently, There is growing concern regarding the toxicity in lead-containing devices driven by the result of restriction of hazardous substances directive regulations. To address this concern, there has been a resurgence in the compositional development of lead-free piezoelectric materials. Sodium-potassium niobate K, Na, NBO3. This material is also known as NKN. In 2004, a group of Japanese researchers led by Yasuyoshi Saito discovered a sodium-potassium niobate composition with properties close to those of PZT, including a high. Certain compositions of this material have been shown to retain a high mechanical quality factor with increasing vibration levels, whereas the mechanical quality factor of hard PZT degrades in such conditions. This fact makes NKN a promising replacement for high-power resonance applications, such as piezoelectric transformers. Bismuth ferrite, BFeO3, is also a promising candidate for the replacement of lead-based ceramics. Sodium niobate Now NBO3, bismuth titanate B403012, sodium bismuth titanate Now 0.5 B0.5 TO3. So far, neither the environmental impact nor the stability of supplying these substances have been confirmed.
Polymers.
Polyvinylidene fluoride, PVDF. PVDF exhibits piezoelectricity several times greater than quartz. Unlike ceramics, where the crystal structure of the material creates the piezoelectric effect, in polymers the intertwined long-chain molecules attract and repel each other when an electric field is applied.
Organic nanostructures.
A strong shear piezoelectric activity was observed in self-assembled diphenylalanine peptide nanotubes, PNTs, indicating electric polarization directed along the tube axis. Comparison with Li-NBO3 and lateral signal calibration yields sufficiently high effective piezoelectric coefficient values of at least 60 pMv, shear response for tubes of 200 nanometers in diameter. PNTs demonstrate linear deformation without irreversible degradation in a broad range of driving voltages.
Application.
Currently, industrial and manufacturing is the largest application market for piezoelectric devices, followed by the automotive industry. Strong demand also comes from medical instruments as well as information and telecommunications. The global demand for piezoelectric devices was valued at approximately $14.8 billion in 2010. The largest material group for piezoelectric devices is piezocrystal, and piezopolymer is experiencing the fastest growth due to its low weight and small size. Piezoelectric crystals are now used in numerous ways.
High voltage and power sources.
Direct piezoelectricity of some substances, like quartz, can generate potential differences of thousands of volts. The best-known application is the electric cigarette lighter. Pressing the button causes a spring-loaded hammer to hit a piezoelectric crystal, producing a sufficiently high-voltage electric current that flows across a small spark gap, thus heating and igniting the gas. The portable sparkers used to ignite gas stoves work the same way, and many types of gas burners now have built-in piezo-based ignition systems. A similar idea is being researched by DARPA in the United States in a project called energy harvesting, which includes an attempt to power battlefield equipment by piezoelectric generators embedded in soldiers' boots. However, these energy harvesting sources by association have an impact on the body. DARPA's effort to harness 1 to 2 watts from continuous shoe impact while walking were abandoned due to the impracticality and the discomfort from the additional energy expended by a person wearing the shoes. Other energy harvesting ideas include harvesting the energy from human movements in train stations or other public places and converting a dance floor to generate electricity. Vibrations from industrial machinery can also be harvested by piezoelectric materials to charge batteries for backup supplies or to power low-power microprocessors and wireless radios. A piezoelectric transformer is a type of AC voltage multiplier. Unlike a conventional transformer, which uses magnetic coupling between input and output, the piezoelectric transformer uses acoustic coupling. An input voltage is applied across a short length of a bar of piezoceramic material such as PZT, creating an alternating stress in the bar by the inverse piezoelectric effect and causing the whole bar to vibrate. The vibration frequency is chosen to be the resonant frequency of the block, typically in the 100 kHz to 1 MHz range. A higher output voltage is then generated across another section of the bar by the piezoelectric effect. Step-up ratios of more than 1001 have been demonstrated. An extra feature of this transformer is that, by operating it above its resonant frequency, it can be made to appear as an inductive load, which is useful in circuits that require a controlled soft start. These devices can be used in DC-AC inverters to drive cold cathode fluorescent lamps. Piezo transformers are some of the most compact high-voltage sources.
Sensors.
The principle of operation of a piezoelectric sensor is that a physical dimension, transformed into a force, acts on two opposing faces of the sensing element. Depending on the design of a sensor, different modes to load the piezoelectric element can be used: longitudinal, transversal and shear. Detection of pressure variations in the form of sound is the most common sensor application. For example, piezoelectric microphones. Sound waves bend the piezoelectric material, creating a changing voltage, and piezoelectric pickups for acoustic electric guitars. A piezo sensor attached to the body of an instrument is known as a contact microphone. Piezoelectric sensors especially are used with high-frequency sound and ultrasonic transducers for medical imaging and also industrial non-destructive testing, NDT. For many sensing techniques, the sensor can act as both a sensor and an actuator. Often the term transducer is preferred when the device acts in this dual capacity, but most piezo devices have this property of reversibility whether it is used or not. Ultrasonic transducers, for example, can inject ultrasound waves into the body, receive the returned wave, and convert it to an electrical signal, a voltage. Most medical ultrasound transducers are piezoelectric. In addition to those mentioned above, various sensor applications include: piezoelectric elements are also used in the detection and generation of sonar waves. Piezoelectric materials are used in single-axis and dual-axis tilt sensing, power monitoring and high-power applications, for example medical treatment, sonochemistry and industrial processing. Piezoelectric microbalances are used as very sensitive chemical and biological sensors. Piezos are sometimes used in strain gauges. A piezoelectric transducer was used in the penetrometer instrument on the Huygens probe. Piezoelectric transducers are used in electronic drum pads to detect the impact of the drummer's sticks, and to detect muscle movements in medical acceleromeography. Automotive engine management systems use piezoelectric transducers to detect engine knock sensor, KS, also known as detonation, at certain Hertz frequencies. A piezoelectric transducer is also used in fuel injection systems to measure manifold absolute pressure, MAP sensor, to determine engine load, and ultimately the fuel injector's milliseconds of on-time. Ultrasonic piezo sensors are used in the detection of acoustic emissions and acoustic emission testing.
Actuators.
As very high electric fields correspond to only tiny changes in the width of the crystal, this width can be changed with better than precision, making piezo crystals the most important tool for positioning objects with extreme accuracy, thus their use in actuators. Multi-layer ceramics, using layers thinner than 100 ohm, allow reaching high electric fields with voltage lower than 150 V. These ceramics are used within two kinds of actuators: direct piezo actuators and amplified piezoelectric actuators. While direct actuators stroke is generally lower than 100 ohm, amplified piezo actuators can reach millimeter strokes. Loudspeakers, voltage is converted to mechanical movement of a piezoelectric polymer film. Piezoelectric motors, piezoelectric elements apply a directional force to an axle, causing it to rotate. Due to the extremely small distances involved, the piezo motor is viewed as a high-precision replacement for the stepper motor. Piezoelectric elements can be used in laser mirror alignment, where their ability to move a large mass, the mirror mount, over microscopic distances is exploited to electronically align some laser mirrors. By precisely controlling the distance between mirrors, The laser electronics can accurately maintain optical conditions inside the laser cavity to optimize the beam output. A related application is the acousto-optic modulator, a device that scatters light off sound waves in a crystal, generated by piezoelectric elements. This is useful for fine-tuning a laser's frequency. Atomic force microscopes and scanning tunneling microscopes employ converse piezoelectricity to keep the sensing needle close to the specimen. Inkjet printers. On many inkjet printers, piezoelectric crystals are used to drive the ejection of ink from the inkjet print head towards the paper. Diesel engines. High-performance common rail diesel engines use piezoelectric fuel injectors, first developed by Robert Bosch GmbH, instead of the more common solenoid valve devices. Active vibration control using amplified actuators. X-ray shutters. XY stages for micro-scanning used in infrared cameras, moving the patient precisely inside active CT and MRI scanners where the strong radiation or magnetism precludes electric motors. Crystal earpieces are sometimes used in old or low-power radios. High-intensity focused ultrasound for localized heating or creating a localized cavitation can be achieved, for example, in patient's body or in an industrial chemical process.
Frequency standard.
The piezoelectrical properties of quartz are useful as standard of frequency. Quartz clocks employ a crystal oscillator made from a quartz crystal that uses a combination of both direct and converse piezoelectricity to generate a regularly timed series of electrical pulses that is used to mark time. The quartz crystal, like any elastic material, has a precisely defined natural frequency, caused by its shape and size, at which it prefers to oscillate, and this is used to stabilize the frequency of a periodic voltage applied to the crystal. The same principle is critical in all radio transmitters and receivers, and in computers where it creates a clock pulse. Both of these usually use a frequency multiplier to reach gigahertz ranges.
Piezoelectric motors.
Types of piezoelectric motor include the traveling wave motor used for autofocus in reflex cameras, inchworm motors for linear motion, rectangular four-quadrant motors with high power density, 2.5 watts per centimeter 3, and speed ranging from 10 nanometers per second to 800 millimeters per second, stepping piezo motor, using stick-slip effect. All these motors, except the stepping stick-slip motor, work on the same principle. Driven by dual orthogonal vibration modes with a phase difference of 90 deg, the contact point between two surfaces vibrates in an elliptical path, producing a frictional force between the surfaces. Usually, one surface is fixed causing the other to move. In most piezoelectric motors, the piezoelectric crystal is excited by a sine wave signal at the resonant frequency of the motor. Using the resonance effect, a much lower voltage can be used to produce a high vibration amplitude. Stick-slip motor works using the inertia of a mass and the friction of a clamp. Such motors can be very small. Some are used for camera sensor displacement, thus allowing an anti-shake function.
Reduction of vibrations and noise.
Different teams of researchers have been investigating ways to reduce vibrations in materials by attaching piezo elements to the material. When the material is bent by a vibration in one direction, the vibration reduction system responds to the bend and sends electric power to the piezo element to bend in the other direction. Future applications of this technology are expected in cars and houses to reduce noise. In a demonstration at the Material Vision Fair in Frankfurt in November 2005, a team from TU Darmstadt in Germany showed several panels that were hit with a rubber mallet, and the panel with the piezo element immediately stopped swinging. Piezoelectric ceramic fiber technology is being used as an electronic damping system on some head tennis rackets.
Infertility treatment.
In people with previous total fertilization failure, piezoelectric activation of oocytes together with intracytoplasmic sperm injection, ICSI, seems to improve fertilization outcomes.
Surgery.
A recent application of piezoelectric ultrasound sources is piezoelectric surgery, also known as piezo surgery. Piezosurgery is a minimally invasive technique that aims to cut a target tissue with little damage to neighboring tissues. For example, Hoyne al. reported its use in hand surgery for the cutting of bone, using frequencies in the range 25 to 29 kHz, causing micro-vibrations of 60 to 210 mm. It has the ability to cut mineralized tissue without cutting neurovascular tissue and other soft tissue, thereby maintaining a blood-free operating area, better visibility and greater precision.
Potential applications: photovoltaics.
The efficiency of a hybrid photovoltaic cell that contains piezoelectric materials can be increased simply by placing it near a source of ambient noise or vibration. The effect was demonstrated with organic cells using zinc oxide nanotubes. The electricity generated by the piezoelectric effect itself is a negligible percentage of the overall output. Sound levels as low as 75 decibels improved efficiency by up to 50%. Efficiency peaked at 10 kHz, the resonant frequency of the nanotubes. The electrical field set up by the vibrating nanotubes interacts with electrons migrating from the organic polymer layer. This process decreases the likelihood of recombination, in which electrons are energized but settle back into a hole instead of migrating to the electron-accepting ZNO layer.